I guess it's about time to start. Welcome back, everybody. I hope you've had a somewhat relaxing break. I will actually just take off from where we left it last time, although we did actually reach a big important point. So it'll be worth repeating that conclusion. So most part of last lecture really was spent to, in some sense, tie down the main conclusion at the classical level of our symmetry-based approach. Okay, so we had the symmetry-based approach where, remember we were essentially insisting on, say, Lorentz symmetry of the S matrix, which also had to be unitary and had to give rise to local and causal physics. And we came to the really very strong conclusion that because of the resulting diffeomorphism symmetry, basically we were given this bit here. So we were given essentially what I call here linearized Einstein-Hilbert EH. And then I showed how to argue that once you couple the graviton to its own energy, okay, which is the only consistent way of coupling the graviton to itself, as we argued, we actually were led to an infinite series of couplings which involve increasingly higher powers of the graviton. So for example, we first constructed a 3-graviton vertex, then we constructed a 4-graviton vertex, and so on. And we argued that this is order by order the same as the expansion of full nonlinear Einstein-Hilbert around, of course, asymptotically flat space, right? So, however, I went further and I said that one can argue, one can show that this whole sum actually gives you the full nonlinear Einstein-Hilbert. And so the conclusion was, it's here repeated, that what our symmetry principles give us are at the 2-derivative level, the unique classical theory that we can base, that we can build, is actually Einstein-Hilbert. And so another way of saying it is obviously that the low energy interactions of the graviton, so two derivatives, are extremely highly constrained. And the graviton, of course, when I used the word graviton, we were very careful what we meant in this course. So we, of course, mean the helicity ±2 unitary irrep of the Poincaré group, okay? So as long as we mean graviton, if this is what we mean by graviton, this conclusion, well, up to the other symmetry principles, but this conclusion holds, okay? So please, again, take into account that this is actually a very strong conclusion. However, it is restricted to 2 derivatives and to the classical theory. And of course, where we want to go next is the quantum level. And of course, I will pursue yet again a symmetry-based approach, very much based on the same kind of symmetries. But in order to make progress, I will have to go a little bit more into the details of the machinery that actually allows us to talk about processes that are still at low energies, but now quantum. And so we embarked just a little bit into that journey, and I just sort of gave you a slogan, and today I'm going to put quite a lot of more details on the statement there. So the recipe is basically to go to the quantum level at the level of the discussion that we have, so meaning low energy quantum effects, okay? That we continue to insist on the symmetry principles, but we add to it some very deep ideas about renormalization. And together, this will give us the package of effective field theory, or EFT. And the kind of statement that I want to establish today in detail, in general, and maybe then already we have time to go a little bit more specifically into the case of gravity, but we will first work in generality, is precisely summarized here at the bottom. So if I look at some process as maybe some amplitude for alpha going into beta, then I can write this as an expansion in the energy of the process divided by some characteristic cutoff. Oops, sorry, I deleted this. I didn't want to. Some characteristic cutoff energy, which can be some characteristic mass scale in the problem, such as, for example, in gravity, the Planck mass. And basically, I can arrange it in ascending powers of this ratio of scales. And to each power, I associate some amplitude AN. And the key realization is that we can calculate this AN in a controlled manner, thanks to this structure here that we're going to establish. We can calculate this process to a fixed accuracy that we desire, okay, by using only a finite number of ingredients. So specifically only a finite number of interactions. Those interactions, of course, will be heavily constrained by the symmetry principle in the first place. And so how and why this works is going to be basically today's subject. So we're going to abstract away a little bit from gravity at first, and then we're going to get right back to gravity to show how this is specifically borne out. And then this will not be today, but probably already next week, we will actually use this to calculate some interesting quantum processes in low energy quantum gravity. Okay. So, so basically we're going to start now a discussion of effective field theory, but geared towards the kind of applications that we have in mind. So first of all, let me give you a slightly alternative perspective, which is conceptually useful, I think. So this alternative perspective is that we think of our theory as being organized in energy scale. So we have some line here where we have at the bottom, we have the infrared scale, the low energy scale. And at the top, we have the UV scale, the high energy scale. And we calculate with some sort of sliding cutoff scale. So somewhere there is some intermediate energy. Oh, sorry, when I use colors, again, I should probably have a thicker pen. So there's some sliding energy scale in the middle, which often one calls a cutoff scale. So E is equal to, say, lambda. That's our cutoff scale. Then, okay, our theory will have some states which have masses which are above this cutoff, which are sort of heavy things. And then we have, equally, we have below the cutoff, we have a bunch of states that have lower energies, lower masses than the cutoff, so we call these light. And then the idea is that we, indeed, that we go up here and we integrate out the heavy fields. So we integrate out these heavy fields. And this gives rise to some effective description, which is the low energy effective description. So this generates, what this does is actually, this generates non-local, typically, interactions, or sometimes non-local interactions. So we'll comment more in detail about this non-local. So for the light fields, okay, and really the key point about how RG works is that up to some ways of matching up the high energy physics to low energy physics, those two actually decouple, and I will be able to think about everything that happens at low energy in terms of this effective description. This is the effective field theory, without having to explicitly worry about any of the details about what has happened up here. I can integrate it out, up to a few matching coefficients, I can forget about the fact that this even exists, and I can work with this effective field theory, provided that I only charge myself with making predictions for processes that happen below the energies of the cutoff. So there is a certain sense of decoupling of the physics between scales, and that's really physically the important shall I say, phenomenology of quantum field theory that allows us to do this. Okay, so now let me illustrate this just using a very simple example. So the simple example that I'm going to use is actually the first effective field theory, if you, as it were, that entered the canon of physics, and that's the Fermi theory of the weak interactions. This is the Fermi theory. So schematically, that's a theory that has a interaction that couples four fermions, psi, bar, psi bar, psi. This is very schematic. Will be a little bit less schematic in just a few lines down. So we are in our favorite world in 3+1 space-time dimension. And so in 3+1 space-time dimensions, this fermion, of course, has dimension 3/2. So if I have four of them, I have to couple them with a dimensionful coupling constant. So this is okay. So this is our 4 Fermi coupling here with the Fermi coupling constant, and we have, you know, our 4 fermions here, and obviously the kind of process that was originally described is, for example, something like beta decay, proton, neutron, electron, and the anti-electron neutrino. Okay, but generically, it's just a coupling of 4 of these spinor fields together in 4 dimensions, and so we're going to have to do it with a coupling constant that has dimension. And in fact, because this is real physics, we can actually say from experiment what GF is. So GF is actually happens to be something like 1 over about 300 GeV squared, so 292.9 GeV squared, right? And the fact that it's inverse energy squared, again, you have 4 fermions, each of dimension 3/2, so that gives you dimension 6. So you have to get back to dimension 4. So this GF beta has dimension -2 in energy units. And okay, here is its value, 292.9. Good. So from actually already the preliminary discussion that we had last time, we have actually already said that if a coupling constant has negative mass dimension, we are in some sense in trouble because this theory is non-renormalizable. Okay. Of course, the whole point is that we're going to explain today that this does not mean at all that we're in trouble, but the precise sense of why we are in fact not in trouble is to be developed. Okay, but so from the sort of naive perspective, one might think one is in trouble. But actually, in this case, we can say even less. We're in even less trouble than one might suspect. So not only can we make sense up to a certain cutoff of non-renormalizable theories if we work with an effective field theory. That's the content of what I'm going to explain. Moreover, in this particular theory, we actually know that the theory secretly is renormalizable, and that works because of the work of, for example, 't Hooft and Veltman. Because what we know is that actually this comes from the broken electroweak theory, and the electroweak theory itself is renormalizable. But so how does it work? Well, so we know it comes from the electroweak theory in its broken phase, in broken phase. Okay. So just to go back to our sketch here, what's going on is that I wrote down some theory which we want to interpret as living somewhere here at low energy. But in fact, we know in this particular case where it comes from here at high energies. And so I can show you how this seemingly ill-defined theory comes from something that's perfectly well-defined in the UV in this particular case. And that will illustrate this kind of perspective. However, I also want to again emphasize the fact that, as we will explain, if I hand you this theory and you want to calculate in it, you can do it even without knowing what happened up here. So what I'm giving you in some sense for the electroweak theory is a bonus. We don't even need that, right? We don't need to know that, in fact, in this case, it works up here. But anyway, because this is just the first overview, I wanted to show this particular example, okay? So what is this process? Well, in that theory, you can also have an interaction of 4 fermions, but it's mediated by the exchange of a massive W boson, right? We're in the, how do I get rid of this? Wait. Okay, we're in the broken phase, okay? So you have here the exchange of some W mu. We have our 4 fermions, psi, 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 psi. Let's say we have some momentum P1, P1, P2, we have the exchange momentum P, and then we have P3 and P4. And the relevant term in the Lagrangian that we want to, so again, we're in the broken phase, okay? So this is like, we have a field strength F mu nu squared, but then we have a mass term for this W, okay, which is generated by electroweak symmetry breaking. And then we have the interaction psi bar ID plus G with this W into psi, okay? And so this theory here comes from, this is the symmetry broken phase. This is the broken phase of a Yang-Mills theory, which is actually renormalizable. So how do we find this non-renormalizable Fermi theory within this? Well, let's just write down, roughly speaking, this process. So the amplitude for this process, according to the electroweak theory in the broken phase, is, so we have twice the coupling G. Okay, this is our coupling here. The boson is exchanged between 2 fermions. And then, okay, we have to write some polarizations for the ingoing and outgoing fermions. So we have these polarizations V mu, gamma mu, U1. Okay, this is obviously the ingoing bit here. Then we have the propagator for the massive boson, minus I, eta mu nu, minus P mu over M squared, all divided by P squared minus M squared. Okay, this is just the propagator for the massive W boson, and it has some explicit mass here. Okay, and of course, because it has a vector index, there is some vector structure here. Okay, and then you also have the bit for the outgoing guys, which is U bar 3 gamma nu V4. Okay, this is just standard Feynmanology for this simple Lagrangian here. And as I said, these V's and U's are just the equivalent of like polarizations for the ingoing and outgoing fermions. And we have 4 overall, as you can see. So now the point is that the W boson, of course, so W mu is massive. Okay, so it only propagates a finite short distance. So propagates, or let's say mediates a short distance force. Okay, and so the idea is literally that if we look at low energies or larger distances, we can zoom in on this process. And what happens if you zoom in on this process, you now consider, let's say, scales which are larger than the inverse mass scale of the W boson. Well, these 4 fermions are going to be pulled together effectively, okay? And you get a coupling that looks local of 4 fermions that interact at one effective vertex. And that will be our Fermi theory. And to construct it, nothing easier than that. Sorry, we'll do it in a sec. I just wanted to write one more sentence here. And the point is that mediates short distance force. So at low energies, a point interaction should be a good approximation. So, so in fact, so let's expand. So for, let's say, S, which is p squared, much less than this mass scale m squared, we can just expand. Okay, so we consider now m to be a large parameter, so 1 over m squared is a small parameter, and we just expand this in powers of 1 over m squared, and what we get is we get im is equal to minus I g squared over m squared times v bar 2 gamma mu u1 u bar 3 gamma mu v4 plus I g squared, that's not a nice 2, I g squared over m squared times, and now, okay, there's some structure here, so p slash over m, sorry, p slash over m u1 u3 p slash over m v4, plus of course there are higher order terms. But now the important thing is that, look, this is exactly what we said before. So we started with something like GF, oops. We started with something like GF times 4 fermions, okay? And so what we get is we get some, oh, and GF had dimension 1 over mass squared, okay? So we get here 1 over mass squared times an interaction that involves 4 fermions, plus some correction. We will talk about that correction now, of course. So this is precisely of the form. So we want to say this gives us some lambda EFT for these energies, which is of the form GF. But now let's be a bit more, a little less schematic about, you see, the indices. So what we have here is psi gamma mu, psi bar gamma mu psi, psi bar gamma mu psi. So this is the dimension 6 Fermi interaction. Okay. Plus, then we get some correction, which is of the form GF squared over m squared times psi bar d slash psi, psi bar d slash psi plus blah, blah, blah. And the first thing that we wrote here is a dimension 8 correction. Okay. Which is of order of s squared over m squared. So it's very small as per our assumption. So how come So what do I want to illustrate here? So first of all, of course, what we have here is we started with a renormalizable theory. People were even awarded Nobel Prizes for showing that this kind of theory is renormalizable, namely 't Hooft and Veltman. And then we expanded it for low energies, and we ended up immediately with a leading non-renormalizable interaction, which is of the Fermi form. Plus, we ended up with corrections which are arranged in inverse powers of the scale that serves as the defining sort of cutoff scale for our processes. So we only allow ourselves processes below. And there's this one key point that I wanted to make, which was this notion of non-locality. So what did I mean by that? It means that, you see, so I said something here. This secretly here, I've shrunk to a point, something that in the full theory is a finite distance. Okay, so in some sense, this is really a non-local interaction. And the reason, the way that it manifested in this low energy effective field theory is actually that you get an expansion in ascending number of derivatives here, okay? But of course, the coefficients are determined in a particularly propitious way, such as to recover, once you did the infinite resummation, you actually recover a theory which results from what used to be a local theory at high energies, right? So at high energies, this theory is local, but at low energies, I've allowed myself to shrink down this interaction because it's a finite range interaction. So this was the meaning here, okay, with non-locality. Okay, so fine. So the incentive in words then, so we have the Fermi theory, which is non-renormalizable and seems like we have a problem here. But what we actually see is that we should think of the Fermi theory as the first approximation in an expansion in which we include more operators of higher and higher dimension. And this is what we will call our effective field theory. But moreover, but this is now specific, say, to the Fermi theory, okay, we understand what is the UV completion. So we understand actually where it comes from in the UV. So the UV completion here induces higher dimension operators in the effective field theory Lagrangian LEFT, but at energies below, say, 300 GeV, we can be specific here, these give increasingly small contributions. Okay, and here is the point that I mean by fixed accuracy. So if you want to like have an approximation that is good to characteristic energy divided by 300 GeV squared, well, then you can just include this leading term and you're fine. If you want an accuracy which is up to order of powers to the 4 of that ratio, well, then you better also include this term here. Once you want to have, you know, this power to the power 6, this ratio to the power 6, well, you better include the next correction. And however, the point is that you can calculate at fixed order in the derivative expansion if you want fixed accuracy. I have not given you one crucial ingredient, which we will next develop, which is that this works even if you include quantum loops, okay? But in general, I think you see the structure. You arrange the theory in an expansion in inverse powers of the cutoff, and it allows you to calculate the fixed accuracy by including only a fixed number of operators. But of course, this was the simplest example, and it's in a particularly simple example because we know the full high energy theory, so we can we can work with a liberal amount of hindsight. But in actual fact, most of the time we don't know what the UV is, and in fact we don't even care. And so this is what I want to say now. There's essentially two different uses of effective field theory. So one of them we illustrated now. The second one is the one we want to get at with gravity. So there's basically two uses, two applications for EFT. What's going on? This thing is making, it thinks my S are circles and it converts them into circles. That's mean. So two particular ways of using effective field theory. Okay, so the first is what we did now. The UV physics is actually known and maybe a completely well-defined theory, like some renormalizable local quantum field theory. However, we can still say, well, why bother with all that? Because the simplest way of doing it is actually just calculate with, say, the first two leading terms. So the UV physics is known, but we want a simple way to organize low energy physics. Okay. So that's true in the Fermi theory. It's, for example, also true when you use the Chiral Lagrangian for pion physics. So we know that it's QCD in the UV, but calculating at low energies is, you know, a pain, to say the least. And so in that case, the Lagrangian for the effective field theory is basically, okay, the set of all operators OIN up to a given dimension, which are allowed by symmetry and possibly other constraints. Okay, what do I mean by OIN? What I mean is, let's fix the dimension. So for example, in the Fermi theory, you might say, let's fix dimension 6. That's the leading dimension multiplied by 1 over mass squared, right? So that fixes my n, and then there might be more than one operator. So that's why I put the label IN. So what you do is you write down all operators that you can, which are in this case, Lorentz invariant and local at that dimension. And you give them their arbitrary coefficients, and you go away and you calculate. Okay, so in this case, there was only one operator really. And you notice that it's a Lorentz invariant, of course. But in more generally, there could be more than just this one operator. And in particular, if you want to go to higher accuracy, you have to involve higher dimensions. And if you have higher dimensions, then the possibilities of making contractions and so on and getting the operators that satisfy symmetry and other constraints basically become more ample, and you probably end up with a larger set of terms. But because we actually work in this case in a theory where the UV physics is known, okay, all coefficients of the OIN are, at least in principle, calculable. Via integrating out and RG matching, because you also want to, of course, run them to the scale that is required. Okay, so in principle, you can actually write down all of the coefficients. But I emphasize even here that this is in principle, because in practice, it may even be extremely difficult. Such is the case, for example, in QCD. And then, you know, then even though the UV is known in principle, in practice, you have to resort to other ways of fixing these coefficients. And other ways of fixing these coefficients is what's at the key of the second main way of thinking about EFT. So the first main use of EFT basically is convenience. Okay, we can actually put one slogan here, it's convenience. The second one is necessity. And that's that, in fact, we use a context in which the UV physics isn't even known. So the UV physics is not known, but we are content, or we just want to perform calculations up to given Emax, or some cutoff lambda. So of course the prime example here is quantum gravity. Sure, we have some leading theories for what it actually looks like in the UV. I mean, notably string theory. But in fact, sorry, I'm getting these notifications. Okay. Actually, in practice, we don't even care if we talk about low energies, because as you will see, there's going to be a predictive framework that allows us to actually calculate low energy quantum processes in gravity. And the reason why it works is precisely this EFT logic, that we can isolate ourselves from what happens at high scales using this integrating out procedure, and the fact that the high scales then up to some small number of coefficients actually decouples from the high energy physics. So in this case, we have that the Lagrangian of the effective field theory is, well, interestingly enough, exactly the same. Allow me to write this, okay? It is exactly the same mathematical object as this. In other words, all operators OIN up to a given dimension allowed by symmetry and constraints. But the big difference is, of course, in the second point, that now I cannot go ahead, even in principle, and calculate, okay? So the coefficients of OIN, which are a finite set for any finite accuracy, okay? This is the important thing, okay? They must be fixed. Must be fixed by comparing to experiment. Well, this is a slightly too general statement, but still, let me write it like this. But the point, of course, is since it's a finite set of coefficients, I can fix everything I need by a finite number of experiments, and then the theory becomes fully predictive. So in both cases, and this is the technical point that we're going to make. Everybody, I have a question. Are you getting a reasonable reception? Could somebody reply, please?
We are getting a lag somehow. At least I'm getting a lag.
Yes, because I was just warned that my internet connection is unstable. Has this been going on for a while?
No, it's just the last few seconds.
Yes.
Okay. Well, then let's hope that that was just a little slump. So I'm going to go on. Okay. So
I had a question.
Yes. Can I just write that sentence?
Oh, sure.
Yeah. Both cases, we can calculate loop processes. So quantum corrections. Okay, and the point is that therefore, in that sense, in the guise of EFT, even a non-renormalizable QFT is predictive. So in the EFT sense. And so all of what I have said so far, I think makes complete sense to you. Probably you all know this all, that's beside the point. Makes complete sense to you, except perhaps the loop part, because we haven't actually shown how the loop part works. The rest of it you've already seen, right? The tree part we've already seen essentially with the Fermi theory. But the fact that you can also do loops will be what I want to show in detail how it works, and that will be where we go next. But and please, Arunaba, you had a question. Please go ahead.
Yes, I just wanted to know what you made 2 points, like all coefficients of ON are in principle calculable via integrating out and RG matching.
Yeah.
So what is RG matching?
Well, that you want to calculate them, but also they slide. You know, there are basically couplings which run with RG. So you need to also run the RG down to the scale where you match them, the coefficients.
Okay.
Good. So non-renormal QFT, both cases can calculate loop processes. Non-renormalizable quantum field theories also are predictive. Okay, and the upshot even that we will find is that some loop corrections important loop corrections only depend on lowest order LEFT. What do we mean by lowest order? The lowest number of derivatives. And moreover, it can be clearly isolated in computations, I mean. Okay. And this is what will allow us to make unique quantum predictions for, oops, off, for gravitons. So we will arrange basically all of what we've learned so far as the lowest order of an EFT. Then we will systematically classify what can happen at higher orders. And then I will show you how to find specific quantum processes, which in fact, even at the loop level, only depend on those things which we have already uniquely fixed by our symmetry principles. So we're going to, well, first of all, develop this machinery of EFT at the loop level. And then we're going to really go and use those symmetry principles to great effect and calculate, as I said, quantum corrections to gravitational processes, which are unique predictions of all these symmetry principles that we have developed. And of course, that's a very powerful thing, because they are, you know, we know that at low energies we have Einstein-Hilbert. I mean, experiments are getting better and better to convince us that this is the case. And so we can make some quantum predictions just based on that. And those are extremely powerful and stringent tests of any idea you might have about quantum gravity, because no matter what happens in the UV, whether you like strings or, as I said, asymptotic safety or any number of other approaches, they better reduce at low energies to these predictions, because those predictions are uniquely fixed by what we already know. Okay, so let me just finish this first part by saying preview for gravity. Okay, so what we're going to do is we're going to add terms in an expansion in derivatives. So the lowest one, of course, is the infamous cosmological constant. Then we will see that our Einstein-Hilbert term here, this is the unique two-derivative term that we can write down, but this will be corrected by higher derivatives. So for example, things that are like the Ricci scalar squared with some coefficient A1, something like the Ricci tensor contracted, okay? and so on, plus, okay, then you can go to the next derivative level. So you can put like r cubed, and then of course you can also include things like derivatives acting on r, plus dot, dot, dot. There's obviously a very complicated zoo of objects that you can write down. And we will learn how to navigate this zoo specifically for gravity, okay? But the idea is that you write down everything that's allowed by your symmetries. So in particular, right, we have here already imposed this diffeomorphism symmetry. And you arrange it in ascending order of number of derivatives. Okay, so we will now learn. We will learn how to, let's say, tame the zoo of these terms, and to calculate with such a theory. So that's a good time to stop for questions.
I have a question.
Yeah.
If you could you go back a couple of slides to the place where you wrote down the expansion for the Fermi term, like the Fermi term, and then this, yeah. Is it possible to show by such a constructive fashion that you can get the electroweak theory by some constructive method by trying to cancel the non-renormalization, non-renormalizable loop diagrams by putting in higher terms here?
Yeah, that would be nice. I don't know. I suspect not.
Okay, so in that case, you can do a desert kind of analysis and show the uniqueness of electroweak theory.
I don't think so. And but I mean, this is the slogan that we're always being told, which is that what we know, for example, because of this electroweak theory, we know that some new physics has to happen above the electroweak scale, but what it is, we don't really know. I mean, I suppose right now we already know that that this is non-unique, right? Because you could have like the standard Higgs, but then also you could have like Technicolor and so on. Of course, those things have experimental signatures, but I don't think we have enough mathematical structure there to construct. I mean, yes, I'm pretty sure we don't, because already we have these two examples, like Technicolor and electroweak and so on. But we have, I think, some BSM people that are sitting in this course. They probably have better answered this. Do you guys know this? I mean, obviously, it's not unique. We know that, but is it at least sort of you can probably reduce it to a finite set of possibilities, or is even that too optimistic? Okay.
Thanks.
Okay, so it's time to continue. So this was a somewhat detailed overview of this EFT idea, and now let's really get into the meat. So what we're going to do is we're going to properly power count amplitudes. So this is basically to answer the question of what terms to include in lambda EFT once we have specified the accuracy that we're interested in. So this is the answer to the question. So what terms to include in LEFT for a specified accuracy. And so now let me just introduce some notation that will be useful. So now I'm going to specifically label the operators as OID, where this is the set of operators So it's operators with d derivatives. So we're now being specific about the number of derivatives. And with I powers of the fundamental field. Okay, what do I mean by fundamental field? So for example, this would be and will be h mu nu. And so now we're going to write, let's say, the interacting part. So of course the free part is always there and gives us our propagator, but then there is also going to be the part with interactions of our EFT. And we're going to write this as a sum over ID of coefficient CID for each of these operator, made up by the mass dimension D, OID, and in order to get the overall mass dimension to be 4, we put some coefficient f to the 4 here. So we have some overall scale. Okay, so to get, well, let's be, okay, to get L is equal to 4. So for example, okay, this was done by GF, the Fermi constant, in the case of the Fermi theory. And then here we weight this by the powers of M so as to make, oops, comma, so as to make the CID dimensionless. So for example, this was the weak mass scale in the Fermi example. Okay, we had both the GF squared and we had the weak mass scale, which also came, the high derivative terms, the d/d/ terms, they came with powers of the mass scale. Okay, so that's one ordering principle. And then let us write this as f to the 4th times sum of, and then we write actually ON, which depends, it's the operator that depends on our fundamental field. Let's call it schematically phi, why not field phi, divided by V, okay, with Cn m to the dn. Okay, so this is some other way of thinking about this. So fundamental field, where did I write fundamental field? Powers of M system loop. Oh no, okay. So we have to call this fundamental field. Can't just draw some error. Okay, and then this V is some scale to soak up the dimension of phi if it has a dimension. So this could be our mass scale of the symmetry breaking, or it could be, for example, the Higgs wave, or some other scale that floats around. These coefficients, of course, so this is just a different way of organizing it, right? I'm happy to stay with the CID, but the point is that these CIDs and the Cn, they are dimensionless numbers which label our expansion, and those things are generically order 1 numbers. So this is a statement, basically a statement of the fact that these are order 1 numbers is precisely the statement which nowadays, of course, is very controversial, but the statement of naturalness. Okay, so let us not make any philosophical comments here. Let me just say that this is the statement of naturalness. So if you write down these terms, right, we write them down because we are allowed to write them down. Remember, we have to write down all of these operators that are allowed by our symmetry principles and any other constraints. And then the statement of naturalness, which maybe we'll comment on a little bit later, but the point is that the RG perspective that we're using basically suggests that any coefficient that can enter, and will enter so with a coefficient that is expected to be of order 1. And that's all there is to say for now. Oops, I have forgotten to go on the single page view. Okay. So for example, okay, so I think the easiest will be, and this is sort of how I'm arranging the presentation of this lecture, I'm going to write things down that look very schematic and maybe abstract, but then I'm always going to illustrate them with specific examples. And it's, I think, at least for me even, usually only once you think about the examples that the general thing starts making sense. So here, one example is, so let's write some LEFT term. So our might contain something like a term f to the power 4 times 1 over m squared times 1 over v to the 4 phi, two derivatives on phi, okay? And so this illustrates, by the way, the different ordering principles, okay? So this v parameter here counts the number of times that the fundamental field enters, and the mass scale counts the number of derivatives, 2 here. And then we always have this f to the 4 that makes, basically takes care of the overall mass dimension of the Lagrangian. Okay, so this is something which has two numbers of 2 derivatives. So k is equal to 2. We have I, the number of fundamental fields, is equal to 4. And the dn, so the number of derivatives, well, it's equal to 2 here. And so this, for example, gives you, you can look at diagrams. So this can contribute to diagrams of the form. You can have some loop, okay, where 4 of these, at each of the vertex, 4 of these phi fields meet. But for each of these vertex, you also have to include a factor of the momentum that goes through the vertex squared. And that's because you have this d squared here, okay? So this is some sort of phi to the 4 interaction, but instead of just having the field at the vertex, you also have 2 powers of momenta.
Excuse me?
Yes.
So what was the an analog of V in Fermi theory?
In the, yeah, so in the, for example, the Higgs mass, that's what I wrote, as the Higgs wave, excuse me.
I see, okay. But we didn't write it last time, right? When we wrote down the 50.
No, we didn't. So that we basically subsumed it in the weak mass. Yeah, I agree.
Okay.
So now let's go and organize. So okay, but sorry. So the point was that we write down diagrams like this, but we can of course write down all kinds of diagrams. And now let us organize the diagrams in some systematic fashion. So obviously this term can contribute to all sorts of diagrams, but we want to find some ordering principle which allows us to basically systematically organize the theory by energy scale. So we have some amplitude which depends on a certain number, nice E of external particles, and that happens with some energy scale E. So we have our usual kind of drawings. We have some process that happens at energy scale E. We have N alpha, N beta. And by the way, sorry, just so you don't get too lost, and we will identify a better way of saying it happens at some energy scale E in the process of this development now. Now the nice E, curly E, is N alpha plus N beta is the number of external particles. So number of external states. Okay. And so the interaction vertices that we have in the EFT, they generate diagrams that we can identify by, say, the number of lines that meet at a given vertex. So we have, a bunch of lines and more of them, and say k powers of momentum. Okay, so we have I lines and we have k powers of p. So this comes from a term. I is the number of fundamental fields in the term that is in the LEFT interaction. And k is the number of derivatives in this term. And what I want to say is that this is a vertex of label ik. Okay, and so for example, we're going to use in just a moment, we're going to use something like we're going to use VIK, which is going to give us the number in any given diagram of vertices of type ik. But the vertex of type ik is simply this object here, where k lines meet with a total power of momentum p to the k. And of course, we also had, basically, we've already drawn this thing here, but this is what we call an internal line, or just a line, I suppose, which is given by the propagator, which comes from, of course, the kinetic part of the EFT Lagrangian. So then what we will do is we will consider some diagram. Okay, now let's consider some diagram. Let's consider some diagram which has a total number I of internal lines, which has a total number L of loops, and which has VIK, which is the number of vertices of type IK. So for example, okay, again, our diagram above, p squared, okay. I could have written this. Okay, this has, well, it has I is equal to 2, these two internal lines. It has one loop, and it has V 4,2 is equal to 2. Because it has two of these vertices, well, it obviously has this one loop, and it has these two internal lines. Okay, so this is just a way of counting ingredients in a diagram. So now for a general diagram then, so now we're going to start counting factors of momenta, and then of course, as you know, for each loop, there will be one integration over the momentum. And so we're going to basically assemble now this idea of what I called the degree of divergence before, but we're now going to be more systematic about it. So we have a total vertex contribution. So all the vertices in a given diagram, they contribute to the value of that diagram the factor of, I have to take the product over all vertices. And for each vertex, I'm going to have a factor of, well, I times 2 pi to the 4, that's just convention. Then I always have conservation of momenta at the vertex. Okay, all the momenta that go to the vertex should be conserved. Then I have P over M to the power K. So I'm going to, of course, specifically take the product over vertices of type IK. And so because it has K momenta, I'm going to get P over M to the power K. And I'm going to get, so I'm going to get F to the 4, okay, because remember that each of these things had, each of the vertices has an F to the 4 here. Okay, so for each vertex, I'm going to get 1 power of F to the 4. And I'm going to get V to the power I, because V, if you want, is a way of counting the number of fundamental fields that are in there. So there's I of them in each, okay? And all of that goes to the power of VIK, right? So if I have 2 vertices of type 4, 2, then this diagram will have the product of V42, oops, sorry. I have the product of V42 from this and V42 from this, okay? And each of them has momentum conservation at the vertex, and it has these factors here explicitly. We'll write down, by the way, of course, all of this will be illustrated by various examples of this kind below. But okay, I think that this makes sense to you. Okay, and then you have to take the product over all vertices that appear in this diagram. And each of the vertex gives its own contribution. So you raise each of these contributions for a vertex of type IK to the power of how many vertices you have in a diagram of given type IK. That's all this is saying. So product is, so of all types of vertices, product over all types of vertex. Yes, it doesn't never works so well writing down there. So all types of vertex. And then, okay, the other, this is just momentum is conserved. Okay. Momentum is conserved. Okay, we could, of course, derive this momentum conservation in the usual way that you derive it when you derive Feynman rules, but I think you believe me that this is true. Now, for each internal line, you get a contribution. You get a contribution which is basically, well, propagator, right? So I d4p over 2 pi to the 4th, again, there's some convention, but then you get 1 over p squared plus m squared. And then if you think about it, you invert basically. So what you have f to the 4 for the overall scale, you have v squared because there are 2 fields, and you have m squared because there are 2 derivatives. Okay, check. Fine. So now, now these momentum conserving delta functions here are of course important because they allow us to do a certain number of integrals. So we then integrate over the delta 4 p nu of all vertices. And what we're going to end up with is there remain, of course, only the loop integrals. And how many are there? Well, I'm just going to write it now. I think we're going to explicitly convince ourselves in just a few minutes that this is correct, but this basically the number of internal lines minus sum over ik, vik plus 1 loop momenta to be integrated. And so then we get our amplitude A with E curly E external particles at scale E, which we write as the overall momentum conservation, which we factor out of the external momenta, times this, let's say, amplitude E which is the same thing. I've just factored of this factor here, and one sometimes calls this kind of thing a reduced amplitude. But I just define for you what this means. And so now we focus on a tilde E curly of E, and we will do this integral. So actually what I'm proposing to do is can do this integral. Using dimensional regularization, dimreg. So what I propose to do is going to write down the answer for you in general. I'm actually going to leave it as an exercise to do it, but I will do it in 2 specific examples, which I think is actually more useful. Okay, I will explicitly do this in 2 specific examples, and the general case you will then please just do in your own spare time. This is really just a bookkeeping exercise. How many powers of momenta do you have, and how many inverse powers of the propagator? And then these integrals are actually of the type, you know, p squared to the power beta over p squared plus m squared to the power alpha, and they can be done in terms of gamma functions, and then you need to expand these gamma functions. That's not a great deal of fun, and I think it is really more enlightening if we do it in specific examples instead. But in the general case, I mean, I can write it down, but I have it right there in front of me, but I don't think that it will be particularly enlightening for you. I might just include it in the notes that I put on Moodle. So we have L factors of the momentum integration, okay, L, and then we have something like p to the x, where I will write down what x is. So there's x powers of momentum in the numerator, and then there is something like p squared plus q squared to the I in the denominator. So this is the powers of p squared loop momenta in the denominator, and q is the largest of the external momenta. In the 2 examples, please actually hold on for a second. In the 2 examples that I'm showing you, it really will become clear why I can actually put the largest external dimension here, and why that will play actually the important role of the external scale. So actually maybe let me, just because this equation otherwise won't make much sense, maybe just let me call this AE of Q. And so in dimreg, that thing will go like 1 over 4 pi to the power 2L, and then we have Q to the power Y, where, okay, X is the sum over all vertices of type IK, K, V, IK, and where Y is a specific function of the number of loops minus the number of the internal lines plus this factor of K, V, IK. So just to orient you a bit, so what's actually going on here? The point is that at the moment we're just doing some kind of fairly mindless calculations, which is where we are being more specific about what is the divergence associated to these diagrams, and in dimreg, how does it depend on the external scale? And how does it depend on the external scale is important, because this is precisely what allows us to say this would this kind of diagram will contribute to a process at the order, you know, external scale to a given power, and it contains so and so many factors of VIK and so on, which is precisely the ordering principle that we're trying to establish. So once we've put these things more in place, okay, there will be this sort of forest of trees, which basically is how do powers of momenta depend on L, I, and VIK. And we will then pare down this forest, and we will be left with some expression that will allow us to look at the given interaction vertex and see what kind of powers in the momentum expansion it can possibly contribute to. Okay, just to try and give you a little bit the path that we're taking. Okay, so the point will be, we identify now generically for interaction vertex that can be in the EFT expansion, what kind of dependence on the external energy scale can it possibly contribute to? Okay. So far, as I said, it's a bit of a forest of numbers and so on, but we're about to pare it down, and we're going to get to some useful point very, very soon. So, so let's massage these things a little bit. So this reduced amplitude E of Q a little. So we have some useful identities. So for this, we can actually use some useful stuff. A, we actually have that 2I plus E should be equal to sum over I V I K, sum over IK. This is actually totally simple, because all this is saying is that the total number of ends of propagators ending on vertices, written in two different ways. Okay, so consider, for example, this kind of thing. So let's say we have some diagram, okay, which has some external lines and some internal lines. So particularly is external, internal. Okay, and at each vertex, okay, so each internal line necessarily has to start at a vertex and finish at a vertex, while each external line only has one of its ends on a vertex, and the other one is this external thing left hanging. Okay, so twice the number of internal lines plus once the number of external lines is the total number of ends of lines that end in vertices. Okay, so for each internal line, it has to end on 2 vertices, and each external line only has to end on 1 vertex. But the number of lines that go into a vertex also is the sum over I times the number of vertices of type VIK. So summed over all vertices. So this equation just will allow us to reduce clutter a bit by replacing terms of this kind with something that's much easier and just a function of I and E. Okay, and it's just total triviality, right? External line has one of its ends on a vertex, internal line has 2 of its ends, both of its ends on a vertex. Okay. B. Oh, number of loops. Well, we've already said that. 1 plus I minus IK VIK. This is the definition of numbers, of the number of loops. And it's just basically the number of integrations that you can do subject to total momentum conservation over each of the vertices which have local momentum conservation. A little bit of thought convinces you that that's given by the number of internal lines minus the total number of vertices plus 1. And this plus 1 is precisely because you have 1 overall momentum conserving delta function that will be left. And then the largest external scale, well, this is just what we called Q. Okay, I said this before, but Q is what we call the largest external scale. Please, for this, in order to see this, you should have a bit of patience. Just a few minutes. Largest external scale. Okay. So then, going back to our expression here, so this thing here is a statement about how in dimreg, the finite part of this integral scales with Q in terms of, as you can see, the kind of expressions that we just discussed. So once you use all this, now we're paring down the forest. This means that this will behave like f to the 4 times 1 over v to the number of external particles times m squared over, well, there's some 4 pi here, but we really don't care, f squared to twice the power of momentum times this q over m to the power p. And p will be written down in a second. So p is equal to 2 plus 2l plus sum over ik of k minus 2 vik. Okay, so right. What has happened? I'm just repeating myself, but I think really I just want to go on to these examples because that will illustrate it more. And then once you have understood the specific examples, I really urge you to go back and just do the same kind of manipulations for this. So there's 2 things that you still need to check, which I think is just too much detail for the lecture, but you need to check that this integral here in dimreg does indeed give you this dependence on the external scale. And then with my definition of y here that I've given you, and my definition of x that I've given you, apply as much as you can those kind of definitions, okay, where of course you also take into account the factors of f and m that I have told you come in for each internal line, and that I have told you come in for the total contribution of the vertices. So putting those things together will give you this expression for E. Sorry, I've made the same mistake. Q. Okay. Yeah. And crucially this P. But now let's just abstract from these sort of painful manipulations, and let's just see why this is an important result. Then we'll do the 2 examples, and hopefully that will also make the manipulations look like they're less painful. So, but because it's really, this is the key result, okay? This thing here with this definition of P is the key result that is really important to conceptually understand. So let's look at the implications of this result. What are the implications? Well, let's say we fix a certain degree of accuracy. So how do we achieve this? We say we work at an energy Q that is, let's say, much less than the scale M, and fix some power Q over M, so that gives you the desired level of accuracy that you want. Okay, so in fact, let us call this power P, because we know that a given diagram now, right, it contributes to the amplitude with this power P. So let us fix this P, okay? And then this means, okay, we get contributions from tree diagrams, meaning no loops, okay, such that we have to have that sum over ik of k minus 2 vik is equal to p minus 2. Okay, that's just rewriting this formula here. Okay, P minus 2 is equal to 2L plus K minus 2, sum over K minus 2 times VIK. And we said, if we set L to 0, then we end up with this equation. So these are all the zero loop contributions that we can get. We can get one loop contributions such that sum IK is equal to, such that sum IK K minus 2 VIK is equal to P minus 4. Because now I put in L is equal to 1 here. And so I add a factor of 2, so I get P minus 4 is equal to this sum, etc. But that means that the higher the number of loops, so what happens? So let's say my fixed P is whatever, 4, okay? Now K is the number of derivatives that contribute to my vertex, okay? K is just exactly the number of derivative operators that appear in the operator in the EFT expansion. So if K is greater than 2, which means you're above the kinetic part of the Lagrangian, then this thing will necessarily be positive, okay? So this thing is a finite positive number. So that means that at some point, even if you only have one vertex of a given type, you can't increase the number of derivatives anymore. Okay, so at zero loop, you can cut off the EFT expansion at a definite order K in derivatives. But now the key point is that now you look at the one loop contribution, okay, this cuts off even earlier because the number that is on the right-hand side is smaller than the number for the zero loop. And if you were to go to two loop, this would cut off even earlier. So that means that once you have included all operators up to a given order in the derivative expansion so as to satisfy the first here, there can be no higher derivative terms that would possibly contribute at higher loop order. And so if you work with this finite set of terms, to all loops you can make sense of this theory because you're still working with a finite number of terms. And so there can only be a finite number of counter terms because there can only be a finite number of these divergent structures. Okay, so this is really the key. This means that you can work to a finite order in the derivative expansion of these operators once you've fixed your accuracy of the EFT. And once you're at a finite number, you can just work to all intents and purposes. You can work in this theory as if it is a normalizable theory, because we say a renormalizable theory, because a renormalizable theory is defined by only ever having a finite number of counter terms. An effective field theory is a theory where for a given accuracy, you only have to include a finite number of counter terms. That's it. And then it becomes fully reasonable to work in this theory to all loop order. So this is the conclusion. Only a finite number of operators in a P that is in a derivative expansion contribute at fixed level of accuracy. And that means only a finite number of counter terms is needed. Oops. And so therefore, this EFT is predictive. But always, of course, only for processes which are below, let's say, our cutoff energy, lambda. Now let me, because I only have like 5 minutes left, let me actually do these examples. Okay, let me do these examples, and then I will open the floor for questions of more conceptual nature. But I promised you that I think it is much more enlightening to actually look at examples rather than try to immediately master the general picture. So let's look at something like just box standard 5 to the 4 terms. So we have something like f to the 4. We have 4 powers of the field. We have some coupling, which people like to call lambda over 5 factorial times 5 to the 4. And let's look at the diagram of this kind. So we have momentum P. We have P1 plus P2 here. We have P2, P1, and we have P3, P4 momenta. Okay, so what is this? There are 2 vertices. Okay, I have the ingoing momenta P1, P2. I have loop momentum P, and so momentum conservation means that I can label the internal momenta like this. Okay, that's momentum conservation. And I get, well, I get m to the 4 over v to the 4 times minus I lambda over minus I lambda squared over 2. I guess I've done something about the symmetry factors. Then I get the integration over the loop momentum P. There's only one loop, 2 pi 4. Who cares? Actually, let me make more space. Times I over P squared plus M squared times the second propagator, I over P1 plus P2 plus P squared plus M squared. Yeah, sorry. And I'm integrating over this, which, well, okay, m to the 4 over v to the 4 minus I lambda squared I times v of p squared. So let me calculate this v of p squared that I've defined here. So v of p squared is equal to minus 1/2. I can introduce some Feynman parameter, dx 0 to 1 of d np 2 pi to the n, because I want to do Dimreg, 1 over, and then I have, let me just call this pe squared. I've already gone to Euclidean signature. 1 minus x. This is a sort of Peskin and Schroeder type exercise. P1 plus P2 squared plus M squared squared. So the comments are, this is some Feynman parameter to do this. Okay, standard technique. And then once I've used this Feynman parameter, now what I wanted to say is that you see the external momentum scale that here appears is P1 plus P2, and this is what I want to call my Q. Okay, so this is really the total external momentum that's ingoing into the diagram. Okay, so things arrange themselves such that things will depend on the energy scale Q here. So that's the first example where we see what I mean by there's going to be some external, total external power. And so, well, I can do this and do this computation here. So this integral you can look up will give you some gamma function. Okay, so then as usual in Dimreg, I write this down as a function of the dimension n and analytically continue. And the point is that the finite part of this gives me literally q over m to the power p f to the 4 1 over v to the power epsilon times sorry, m squared over f squared to the 2L, which, well, okay, sorry, I need more space. So let me go on the next page. Copy, paste. So if you actually do this, you get the power q to the 0, and you get m to the 4th over v to the 4th, which corresponds precisely to p is equal to 0 and L is equal to 1. So I'm realizing that I'm running out of time. I do want to write one more diagram. I want to write, just to compare the two, f to the 4 over v to the 4, 1 over m squared times the diagram, which is of the form lambda 4 factorial phi squared box phi squared. So this is almost the same thing, but it has two factors of momentum. And so you write the same diagram, but at each of these vertices, you have two factors of the momentum squared, okay? You still have P, P1 plus P2 plus P. And now, what happens is that V of P squared, now it goes like E over M to the power P, F to the 4, 1 over V to the epsilon, M squared over F squared to the power 2L, where you actually do this thing, you get P is equal to 4, L is equal to 1. Okay, so let's say you want to calculate this process to accuracy. Let's say P is equal to 2. So Q squared over M squared. I'm sorry, why is this? Right? I want to calculate this to order Q over M squared. Then this first type term without the momenta, this guy, it does give a contribution, whereas the second type term, where I have phi squared 2 powers of the derivative phi squared, it gives a contribution which is actually at a higher order in the momentum expansion, because this diagram explicitly goes like Q over M to the power P, where Q is, again, the total power of momenta going in. So this thing will be subleading, will be much smaller contribution if Q is much smaller than M. So we're below the cutoff, much smaller contribution than the first. And so at accuracy P is equal to 2, I don't even have to think about this term. I don't even have to think about including this in my Lagrangian. However, if I do want to be at P is equal to 4, then I have to put in this diagram, but I wouldn't have to put in a diagram with more numbers of derivatives. Okay, excuse me for going over time and the somewhat technical nature of this discussion, but I think it's still worth to open up for questions. Are there any?
Yes, maybe if I get this right, in addition to keeping track of the power P, the power K of the number of derivatives, we also need to keep track of the number of loops when we do computation. It would be wrong to do a diagram with too many loops, I think, or is that correct?
No, I do not think that that's correct. No, you can do as many loops as you want, but they will contribute to lower, a very high loop diagram will actually contribute to a lower power of P than the maximum power that follows from this kind of analysis.
Ah, yeah, right. Okay.
So you can do them, but yeah, you don't need to do an infinite number of them in order to get the fixed accuracy. Yes, I mean, I don't quite know how to say this. I realize that these things are, of course, technical developments, but I'm trying to give you the guiding principles, which is that what we're doing is we're organizing the amplitudes in terms of powers of the external scale. So I think that the one thing that is good about these examples is that this abstract notion of an external scale becomes a little less abstract here. So in this case, both of these diagrams could be written as powers of P1 plus P2. So here the external scale is just literally the total external momentum that is going into the diagram here on this side. Okay, and that's because of the specific form of the propagator. And then, well, I do the Feynman parameterization. And in the end, I can just write it as Q over M to some power P, which is the power that we abstractly determined, where Q is really P1 plus P2. And you see in more complicated diagrams, of course, this might be a more complicated expression of external momenta, but clearly what I'm also saying is that, for example, if one of the external momenta totally dominates all the others, okay, then you can just say Q just reduces to that momentum. And so that's why I use the language that Q is the dominant external scale at some point. So Q will be the dominant external scale, and dimensional regularization of diagrams and careful counting of the loop momenta and the momenta that flow through each vertex allow you to organize the contribution of each diagram in very specific powers of P. And the great thing is that if you're only interested in a finite accuracy, so in a finite order in the Q over P expansion, this kind of ordering principle among all the diagrams actually allows you to establish that only a finite number of vertices in an EFT expansion can ever contribute up to this fixed number of accuracy. And once you've realized that, you just write down the Lagrangian up to a given number in derivatives that is allowed by symmetry principles, and you calculate away. Okay, that's the point. Is that point sort of actually has that point been transmitted more or less clearly?
Yeah.
Yeah. Okay, so good. That's it then. Next time we will go and specifically do this derivative expansion and then calculation of various interesting processes for gravity. So yeah, unless there are any more questions, see you next week.
Okay, see you.
See you. Bye-bye.
Thanks,
Goodbye.
Thank you.
Thanks.